Okay, so let's construct a Taylor series for this 1 over x function, and in this case, let's center it at x equals 2. Okay, so we're kind of playing around with this a little bit, so we need to be a little bit careful with that x equals, let's see, center at 2. So I'm going to generate my polynomial function. Again, I want to figure out the coefficients of this. So I'm going to take the function evaluated at c, so it's going to be 1 over 2. Okay, so that's going to be my a1 function. Okay, let's just, I don't know why my pen is messing around with me, but there we go. So plus my a2. Okay, I'm going to differentiate. Okay, so I need the first derivative of that, which is negative 1 over x squared. Okay, so I'm going to take the c value and square it. Okay, so that's going to be 1 over x squared. Then I evaluate the derivative at the center c, so I'm going to evaluate it at 2. And then just for, completeness, I'm going to put the 1 factorial in there, just so that we don't forget that 1 factorial. And then I'm going to put my power series part in there, x. Okay, so it looks like it alternates. So I'm going to go plus. I'm going to then take the next derivative. Okay, so that's going to be the derivative of that function. So it's going to be negative times negative, which is positive. So I'm going to end up with positive 2 over x to the power 3. Okay, so we're going to increase the power. We're going to take 1 away from the power. I'm going to evaluate that at the center point c. Oops, I don't actually know the number c. So it's going to be 2. And then I'm going to do the divide by the 2 factorial to complete that term, the an term. And then I'm going to make sure I put my power series part. Now, I forgot to do this in my last one, but I have to remember to center it at 2. Okay, so we have to make sure that that power series is centered at 2. Okay, so there's my I should renumber these. Let's call that A0, A1, A2. Okay, so I'm going to move on to A3. And so I'm going to differentiate this function again. So it's a 2 over x cubed function. So that's going to become negative. So I have 2 times negative 3. Okay, and the power becomes power 4 in the denominator. So this is going to be negative 2 over x cubed differentiates to negative 2 times 3 over x to the power 4. I make sure that I put my factorial down there. So there's my an term, and then I'm going to center it, have my power series centered at 2 plus. Okay, oops, and I need to evaluate that derivative at the center x equals 2. So I'll just do one more. I don't think I really need it, but I'm just going to do one more just to practice doing this. So my next derivative is going to be negative 2 times 3 times negative 4, so it's going to be positive. So it's going to be 2 times 3 times 4, and the negative 4, but it ends up being positive. I'm going to do the power rule, so x to the power 5 now in the denominator, and then over 4 factorial. I'm going to evaluate that derivative at c. Oops, and c is equal to 2. We know what c is. And then I need my power series part, so x minus 2 to the power 4 plus dot, dot, dot. Okay, so we can keep going, and we can generate as many terms as you really want. Okay, so there it is. I want to simplify this because I want to eventually, again, the idea is I want to have a sigma notation formula for this 1 over x function. Okay, and so simplifying this becomes 1/2, and this is going to become minus, so it looks like it's alternating. Okay, so it goes minus, plus, minus, plus. The next one should be minus. It looks like here, well, that's going to just be 1 over 2 squared. and then x minus 2. Okay, and it's going to be plus. The 2's are going to cancel out here, so I'm going to end up with 1 over 2 cubed. 1 over 2 cubed. And then this will be x minus 2 squared. Okay, minus. And then the times 2 times 3 will cancel out with the 3 factorial. So I end up with 1 over 2 to the power of 4, x minus 2 to the power of 3. And then the next term is going to be plus. And I think you can see what's going on. The 2 times 3 times 4 cancels with the 4 factorial. So I'm going to end up with 1 over 2 to the power 5. And then the power series part of it is going to be x minus 2 to the power 4. Okay, plus dot 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 dot. Okay, so now once I've got the coefficients, I think the generalizing this doesn't look too bad. I start at 0, so I'm gonna, my p of x function is going to be the infinite series starting at n equals 0. Okay, so we're going to end up with 1/2, and I want to have the 1 in there, so I need to have an n plus 1. It looks like that's true because it had, when n is 1, the power is 2, 2, 3, 3, 4, 4, 5, etc. So that looks pretty good. I need to make it alternate. Okay, so that's another consideration when I come up with my generalization. I'm going to start with positive. So I'm going to go negative 1, 0 is going to be positive. 1 is going to be negative. Every odd one will be negative. Yeah, that looks like it'll work. So that looks like the SN part or the AN part. And then it's going to be x minus 2 to the power. It looks like the powers match the n numbers, so I'm just going to do to the power n. Okay, so there it is. And it looks pretty good because I can see that the power on the 2 and the power on the power series don't match, and they don't match here. They're just one off. So there we go. We have our Taylor series that for that 1 over x function. It doesn't ask for us to test for convergence, sorry, the test for the interval of convergence, but let's maybe do that. I don't know if I can fit that in there, so let's just set up the, I'll just do it separate. So limit as n goes to infinity. And so this is going to be negative 1 to the n plus 1, x minus 2 to the n plus 1 over 2n plus 2 over negative 1 to the power n, x minus 2 to the power n, and then 2 to the power n plus 1. Okay, so there's my ratio test. Starting to run out a little bit of room here, so I need to kind of squeeze it in. I might just go off the page here. So grouping my terms together, limit as n goes to infinity. Okay, so that's going to be the negative 1 parts. I'm just going to end up with a negative 1. The x parts, I'm just going to end up with a x minus 2 in the numerator. Here I'm going to have 2n plus 1 in the numerator, 2n plus 2 in the denominator. So I'm going to end up with an extra 2 in the denominator. And then it looks like that. Okay, so there it is. I have my, I've got rid of all my n's, so I can evaluate my limit. So I'm going to end up with negative x minus 2. So I see the center is going to be at 2. I'm going to move the 2 over to this side. That lets me see the radius a little bit better. So it's going to be a radius of 2. So it looks like my interval of convergence so far is going to be at 0 to 4. Okay, so that's my interval so far. I still need to do a test. Okay, so I'm going to test my endpoints. Okay, so x equals 0. Where's my series here? There's my series here. So when I put an x equals 0 here, I'm going to end up with n equals 0 to infinity. That's going to be negative 2 to the power n, so negative 1 n times negative 2 n, okay, all over 2 to the n plus 1. The fact that this is just going to be positive, but it doesn't really matter because this is a geoseries, so it's going to converge. So we know this is convergent. Okay, so then we can then change that endpoint to equal to. Okay, then we'll test the other endpoint here. Okay, test that endpoint here, x equals 4. Okay, and n equals 0 to infinity again, negative 1 to the n, it becomes 2 to the n. So this is alternating, but again, it doesn't really matter that it alternates because this is a geoseries because we have an exponent in the denominator. Again, this converges. Okay, so then we can change this endpoint into equal to, and there's my interval of convergence right here. Okay, so that represents my interval of convergence. And maybe I'll just label that. Okay, so there we go.